These are the 4.1 lesson activities on vector spaces and subspaces. So consider the set K where every vector looks like A, B, 2 plus B, and A and B are elements of the real numbers. So we're going to list 3 elements in the set K. So you just pick values for A and B and calculate the vector. So let's see, if A and B are both 1, and the third entry would be 2 plus B, 2 plus 1 is 3. Okay, and then another one, if A and B are both 0, then the third entry is 2. Now A and B don't have to be the same, so let's pick A and B different numbers. So let's say 5, -2, and then 2 plus B, so 2 plus -2 is 0. So those are 3 elements in the set K. Is the 0 vector in the set K? So can you choose an A and a B that will give you 0, 0, 0? So the answer is no, right? Because if you choose A and B to be 0, you get 0, 0, 2. And if you want that 2 in the bottom to be 0, then you have to choose the second entry to be -2. So you can't ever get 0, 0, 0. These are the closest you could get, 0, 0, 2 or 0, -2, 0. You can't get 0, 0, 0. There's no A and B that makes that possible. Is K a vector space? No, because it doesn't contain the 0 vector. Okay, let's look at another set, the set of all polynomials of degree 3 or less, and we name this thing P3. T is going to be our independent variable here. List 3 elements of P3. So polynomials of degree 3 or less where T is the variable. So I could say T cubed minus 2T squared plus 4T minus 7. That is a polynomial of degree 3 or less. So it's in the set P3, which is all polynomials of degree 3 or less. Let's see, I have to do 3. So another one could be T plus 4, because that is degree 3 or less. It's degree 1. So let's see, one more could be T cubed minus 8, something like that. Any degree 3 polynomial or less. Is pi t plus root 2 in the set? Yes. Pi is a constant. Root 2 is a constant. So this is a first degree polynomial. It's in P3. Describe P3 using set builder notation. Okay, so it's the set of all things. And the elements in this set all look like degree 3 polynomials or lower. We just don't know the coefficients. So it's going to be AT cubed plus BT squared plus CT plus D, such that A, B, C, and D are elements of the real numbers. Convince yourself that P3 satisfies the 10 properties of a vector space. That is, convince yourself that this acts like a vector space, kind of like R4. Okay, so one of the most important ones that we typically check first is, does it contain the 0 vector? So in this case, we could let A, B, C, and D all be 0 because 0 is a real number. So you can choose all of 4 coefficients to be 0 and you get 0, which, so that is in the set. So 0 is in P3. Check. Okay, another thing that we need to check is closure under addition. So if you add 2 polynomials, let's just pick 2 from up here where I maybe this one and this one, okay? So if you just pick two polynomials and add them together, do you get another third degree or less polynomial? So this would be 2t cubed minus 2t squared plus 4t minus 15. Yep, that's another degree 3 or less polynomial. So this is closed under addition. Closed under scalar multiplication. Let's use this one. If I do t plus 4 and I multiply by a scalar, like negative 3, I get negative 3t minus 12, which is still a degree 3 or less polynomial. So it's closed under scalar multiplication. And then there are 7 more properties to check to make sure that P3 is a vector space, and I will leave that for you to do on your own. I will typically not ask you to do this kind of check all 10 properties kind of question, but it's kind of worth it to do it one time. All right, look at a set H. H is the set of all things that look like at cubed plus bt, such that a and b are real numbers. List 3 elements in the set described. So you just choose an a and a b. So I could have 5t cubed plus 7t. I could have pi t cubed minus root 2t. I could have 3t cubed plus 3t. A and b can be the same number. Is H a subset of P3? So all these things I wrote down, they do live in P3. They are degree 3 or less polynomials. So yes, it's a subset. So now I want to use the definition of subspace to show that H is a subspace of a vector space. Okay, so that means that I have to show 3 things. I have to show it contains the 0 vector, closed under addition, closed under scalar multiplication. So 0. Well, if I make a and b both 0, you get 0t cubed plus 0t, which is 0. Check. So 0 is in H. Okay, 0 is an element of H. 0 is in the set. Okay, now is the set closed under addition? So if you pick 2 elements from your set, maybe this one, and add them together, do you get another element in the set? So I would get closed under addition. I'm going to add them together, and I get 8t cubed plus 10t, and that does also live in H. So that's an element of H. So it looks like it's closed under addition. It seems like that will always happen. Closed under scalar multiplication. So you pick any element. If you multiply it by a scalar, are you still in H? So let's pick 5t cubed plus 7t and multiply it by a scalar. Always good to pick a weird scalar, like maybe a negative, and an irrational number like root 2. Negative root 2 times 5t cubed plus 7t. And then you get negative 5 root 2 t cubed minus 7 root 2 t. That is still an element of H. So it's closed under scalar multiplication. Now we're supposed to prove this again, that H is a subspace of the vector space P3. But this time we're supposed to use the theorem involving span to show that H is a subspace of the vector space P3. So that says that if you can write H as the span of elements from P3, the span of some elements that live in P3, then it's a subspace. So I want to write H as the span of some things that live in P3. So I could say T cubed and T, right? Because the span is the set of all linear combinations. So if I put a coefficient on T cubed and another coefficient on T and add them together, that's a linear combination. So all the linear combinations of T cubed and T would give me AT cubed plus BT. So therefore, H is a subspace of P3. Okay, now we have a transformation T that goes from P3 to the set of 2 by 2 matrices. And we are going to define it as T of P is equal to P of 0, 0, 0, P of 1. So this little p here stands for polynomial, right? Because my inputs live in P3. They're polynomials of degree 3 or less. So I'm going to input a polynomial, and my output is going to be a matrix with 4 numbers in it. 2 of them are zeros, and then 2 of them are outputs of your polynomial function. All right, so find T of 3T cubed minus 2T plus 7. So it's going to be P of 0, 0, 0, P of 1. So P of 0 is what you get when you plug 0 into this polynomial, in which case you get 7. And then P of 1, when you plug a 1 in there, you get 3 minus 2, which is 1, and 1 plus 7 is 8. Okay, find a P other than 3T cubed minus 2T plus 7 that gives the same output, 7, 0, 0, 8. Okay, so P would be, it needs to have a plus 7 to make sure that P of 0 would be 7. But then to get the P of 1 to be 8, I could just do T plus 7. All right, so does that mean that T is onto or T is 1 to 1? So what does it mean if 2 inputs give the same output? That's kind of like how x squared has 2 inputs that give the same output. So let's just think about functions for a second. So f of 2 is 4, but so is f of negative 2. There are 2 different outputs that give the same, so 2 different inputs that give the same output, and that means the function is not 1 to 1. Okay. And then onto, the way we think about onto is can you create every element of the codomain by choosing an appropriate element from the domain to plug in? So can you make every single 2 by 2 matrix, every possible 2 by 2 matrix, like A, B, C, D, and you can put anything you want in those 4. Can you build any 2 by 2 matrix using this rule? And the answer is no, because of these zeros, right? You're always going to have zeros in those 2 spots. You can't build any 2 by 2 matrix, because I could say, build me 1, 1, 1, 1 is not an output from T. And there are many others, right? Many others that you can't build. So, but the question is T a linear transformation? So to answer this, we have to remind ourselves about the definition of a linear transformation. So the definition says that to be a linear transformation, it has to be true that T of U plus V equals T of U plus T of V, and that T of a scalar, C times U, has to be C times T of U. So is T a linear transformation? So if you have two different inputs and plug them into T, is that the same thing as plugging them into T separately and adding? Okay, so let's let U is going to be like an element from P3. So AT cubed plus BT plus C. And V will be another element, DT cubed plus ET plus F. All right, so I'm going to calculate T of U plus V. So you add these together, add U and V together, and you would get T of A plus D, T cubed, plus B plus E, T, plus C plus F. So it's T of all that, okay? And that would be, put the zeros in, P of 0 would be C plus F, and P of 1 would be A plus D plus B plus E plus C plus F. All right, now I have to do T of U and T of V separately and see if I get the same thing. Okay, so T of U, so I'm plugging this polynomial into the formula for T, which is the matrix formula. Put in the zeros. And then P of 0 would be C, and P of 1 would be A plus B plus C. And then T of V, I'm going to plug this formula into the formula for T, which is the matrix thing, 0, 0. And then P of 0 would be F, and P of 1 would be D plus E plus F. And when you add them together, you get C plus F, 0, 0, and then A plus B plus C plus D plus E plus F. So this and this are the same. Okay, so T of U plus V does equal T of U plus T of V. And then I just have to check the scalar thing. T of C times U. Okay, so let's use a different scalar. I'm going to use K because I already have a C. I've already used A through F. So I'm going to use K for my scalar. Okay, so T of K times U, that is KAT cubed plus KBT plus KC, which is plug in 0 into that polynomial and you get KC. Plug in a 1 and you get KA plus KB plus KC. All right, is that the same thing as K times T of AT cubed plus BT plus C? So it would be K times T of 0 is C, 0, 0. And then T of 1 is A plus B plus C. So this matrix is the same as this matrix. When you multiply a matrix by a scalar, you multiply every entry by that scalar, so these two are the same. Okay, so is T a linear transformation? Yes.